Hi everyone, so far we are done with the bending design as well as the shear links design, and what remains is the detailing. Detailing deals pretty much with reinforcement, their percentage, spacing, anchorage length, so on and so forth. Yet I don't find it to be a good idea to skip a significant part of the design, which in fact marks as well the very beginning of the first initial dimensioning of any structural RC member. That is the durability and fire resistance. If you recall part 1, we did work on the trial section and we mentioned something regarding the durability and exposure classes. Let's talk more about them. The design for durability and fire resistance are essential when it comes to the lifespan of any RC building. They are set to confirm building's fitness and protection against any fire incident for a defined period of time. We'll see how to do that later on. By looking at this cross section of a beam, there is the axis distance A, the side axis distance ASD, and the width B. These are needed when assessing members' fire protection. On the other hand, nominal cover plus the grade of concrete along with other measures are parameters to be checked for durability and bond. Both durability and fire resistance will be checked separately later on. But first of all, let's look how they influence the initial sizing of a member. Alright, in a design problem, you might or might not be given the dimensions. For the cases where the dimensions are provided, the overall depth h would be given, as well as the width b. But of course, you design the reinforcement. Since I don't need the overall depth as much as I do for the effective depth d, where in order to find it, h must be subtracted by the axis distance a. Okay? Assumptions regarding the diameters of rebars and links must be made. The nominal cover for durability, however, should be defined. We'll see how to define it in the next slides. However, when determined, the axis distance would be attainable along with the effective depth d. For the cases where span is only given, the initial sizing starts with the SLS requirements. Usually for simply supported beams, L over D is more or less than 15. B is third to sixth of D. H is just an addition of D plus A. And again, the same procedure is followed. You see the nominal cover along with the axis distance are in fact elemental components of the cross section. Now, this was as per the design point of view. It doesn't make it less important though. Let's go through them a bit deeper and understand their importance. Alright, let's talk more about durability and its significance. Basically, we need our RC building not to fall apart even when the strength design is ensured. It can easily be weakened by corrosion. Suppose I design my footing such that I ensure putting reinforcement that will resist the worst ultimate load combination. Yet I failed to put an adequate cover or used poor concrete quality with low grades, and that I ignore the fact that the soil I have designed my footing on is aggressive and permanently wet. By failing to follow the design recommendations for durability, the possibility of rebars getting rusted is very high. No matter how many rebars I put in the footing, they will all get weakened by the action of corrosion, and then the steel I once designed to take care of the ultimate load is no longer capable to do its job due to the high deterioration of its strength. The consequence can be very serious. Of course, it can lead to the collapse of the entire building. Alright, let's just talk about the durability in a bit more detailing. Corrosion of rebars can take action immediately once the passive state of rebar is destroyed. Now, what does the passive state mean? Simply, the passive state is the state where the embedded rebar gains a layer of protection due to the surrounding alkaline nature of concrete. This is the layer of protection, and it plays an important role for the rebars not to start rusting. Yet there are mainly two penetration mechanisms can lead to the destruction of this layer. One is due to carbonation and two is due to chloride attack. Carbonation reaction can penetrate the concrete, digging its way to the rebars, causing the protective layer to give up. This, of course, can adversely affect the rebar in a way it makes it unprotected against corrosion. Yet what is found is that this process rate declines as when providing higher grade of concrete and good concrete quality, along with other measures. And the same story repeats with the chloride attack. Corrosion is the main source of structural failure before attaining the expected life or working life of the building. Yet there is the freezing, thawing, chemical attacks. They must all take into account as well. Now, using higher and good concrete quality, low water cement ratio, good curing, all these tend to decrease the rate of penetration. But the widely and most adapted way to avoid corrosion by providing an adequate cover to the reinforcement, so providing nominal cover. For instance, this beam might have a good and high concrete grade, but the cover isn't that sufficient and it will logically not last as much as this beam does. Now, how to design the nominal cover for durability? Basically, there are two tables. One gives more of a description and another is more technical. It gives the required nominal cover along with other requirements. Here is this table that tells you the exposure class, a description of the class and its subclasses, and some examples. So the table here includes not only 3 classes, but a total of 6 classes. For instance, the XC here is designated for the design under carbonation corrosion risk. This one here. So this is designated as XC. We have XC and its subclasses XC1, 2, 3, and 4. If, for example, my foundation design falls into subclass XC2, then it meets with the description provided in the table. Alright, let's look at the second table. First of all, to fully understand the durability requirements, reference must be made to these documents. You see, it combines both the Eurocode as well as the BS8500. Now, for the case of foundation design exposure class XC2, where wet, rarely dry condition applies, the allowed minimum cover cannot go beyond 25 millimeter. And looking below it, there is the designated concrete grade, which is in this case C2530. So it cannot go beyond it. Now, if I wish to adopt a higher grade of concrete, say class C3240, then 25 also remains the same. But looking at suppose subclass XS2, the minimum cover is 40 millimeter. As for class C2838, so we cannot go below this class. The minimum cover is 40 millimeter. But if I wish to use a greater grade, say C4050, then the minimum cover required reduces to 30 millimeter. So there is this trade-off: increase the grade, use less cover. and vice versa. One important thing is, as you might have noticed, I have been using the word minimum rather than the nominal. And what's given in this table is the minimum, not the nominal. So remember, our aim is for the nominal, not the minimum. So what is the difference between them? Alright, a very simple definition of the nominal cover is the design concrete cover to all the reinforcement, including the links. The nominal cover is the sum of the minimum, the one we saw, plus what's called the allowance for construction deviation. It is said to be 10 millimeter, except when the quality control is approved, it might be taken as 5 millimeter. Okay, let's focus on the minimum cover. Looking at the figure here, you see that we have rebars. Rebars exist, and there's what's called the bond between them and the concrete. Now the forces transferred by the bond between them is ensured if the cover is equal to the bar size. If the minimum cover for bond is equal to the bar size, then at that time I can ensure the safe transfer of the forces, the bond forces. So the minimum cover ensures not only one thing, but two things. Durability, as what we have seen from this table, and it also must ensure safe bond transmission of forces. So what we do in this case is that we take the maximum. It is either going to be the minimum cover for durability or for the bond or 10 millimeter. So basically it cannot go beyond, the minimum cover cannot go beyond 10 millimeter. To make things clear, let's do this example. Now this example is to assess the nominal cover for durability only. Bond is not included. Suppose I want to design the nominal cover for this interior beam. Let's assume the exposure class or the subclass to be XC1. Alright, for the XC1, if you go back to that table, you see it is said to have to be in a dry environment, interior dry environment, and by going back to this table, the minimum cover for the exposure class XC1 is 15 millimeter, corresponding to this grade of concrete, the concrete class. So from this equation, the nominal cover is going to be 25. Remember, this is the construction deviation. It is almost always taken as 10 millimeter, and this is the 15, the one we took it from the table. So the nominal cover is going to be 25 millimeter. Now this was only considering the durability. We'll see in the next slide how to do it for both durability and bond. But first of all, let's look at the footing below, this one here. If the soil is not aggressive, from the same table we can select subclass XC2 for non-aggressive soil. The minimum concrete grade will be C25 if you check that table. So here's the XC2, and the minimum cover is 25, and the lowest concrete class must be used is the C2530. Right. So the nominal cover required in this case is 35 millimeter. Yet this is not true. The code limits the nominal cover for the foundation to 50 millimeter. This is in a case when the footing is casted directly on blinding. Okay, this is unreinforced concrete. If it's casted directly on the blinding, then the nominal cover switches from 35 millimeter to 50 millimeter. Okay, if there is no blinding, then the nominal cover must be increased. So code limits this to 75 millimeter. This is the case where we don't have any blinding. So that means the concrete is casted directly on the ground. Alright, let's now see a more practical example. For the same interior beam, suppose the cross section is as seen, I want to find or determine the nominal cover. And assume that the rebar here has a diameter of 25 millimeter and the link here has a diameter of 8 millimeter. Now from the same equation for the nominal, in order to find the nominal cover here, I'm going to need this equation, of course. And in this case, you see the rebars exist, so I must take it into account. Now the minimum cover here is going to be the max of either, well, I take it from the durability or the bond or 10 millimeter. And we have seen for the durability for the same beam, the nominal cover for only considering durability is going to be 15 millimeter. This is the minimum cover, okay, not the nominal. And the minimum for the bond is going to be what? The bar size. Now the bar size here is 25 millimeter. So which one is greater? Which one is larger? The minimum cover, of course, for the bond. So we take the 25, we just put it back into this equation, and what we find is that the nominal cover turns out to be 35 millimeter. Yet remember, below the rebar is the links, and we have to subtract the 35 millimeter by the link size, that is 8 millimeter. So the nominal cover turns out to be 27 millimeter. It reduces. But when compared with the durability, okay, with this one here, the nominal cover for durability, what we can tell is that the nominal cover for bond is obviously larger than the durability. So we adapt the nominal cover here to be 27 millimeter. And what controls this nominal cover in this time is the bond, since it is greater. The durability was the difficult part. Let's do the easy one. Fire protection. Fire protection of a beam is evaluated by BA and ASD. A should be equal to or more than the nominal cover plus the size of the link plus half size of the rebar. The table shown here applies only to rectangular simply supported beams resisting fire for 60 to 120 minutes, along with 4 optional combinations of A and B. This is the B and this is the A. Of course, there are a lot more details, and reference again must be made to this document. And to understand this table, suppose I want my beam to resist fire for 60 minutes. Then I have 4 alternates. Okay, 1, 2, 3, and 4. I have 4 options. ASD is going to be an addition of A plus 10 millimeter. So if the A, suppose, was 35 here, the ASD is going to be 45. So if I have this cross section with all these dimensions determined, then I just get back to this table, compare the dimensions giving in my actual beam with the dimensions, with the minimum dimensions for fire resistance. And that depends. If I want my beam to resist fire for 60 minutes, 90 minutes, 120 minutes, well, that depends. Of course, increasing the period of time means that you have to use a greater size. Alright, here is my cross section, the simply supported beam that I have been designing. Now to resist 60 minutes fire accident, all alternates are less or equal to my beams A, this is the A, B, and ASD, okay, the side distance, axis distance. So as per the code, my beam will withstand a fire action for 60 minutes. You see, I have 4 options here. The first one meets with the dimensions, with the 3 dimensions of my beam. The B here is 120, but I have it greater than 120. The A required here is 40, but I have it as 50. The ASD is going to be, in this case, just 40 plus 10, so the required one is going to be 50, but I have it here as 52 millimeter. Take all the options, you'll see that they meet with my beam's dimensions. But if I want my beam to resist fire for 90 minutes, then this option doesn't apply to my beam. This one doesn't apply as well, but this one meets, well, the B minimum here is 300. I have my B as 300 millimeter, and the A 40 millimeter. I have the A here as 50 millimeter. ASD in this case is going to be what? The 40 plus 10, so it's 50 millimeter, and I have it here as 52 millimeter. If I want my cross section to resist fire for 120 minutes, then none of the options here meet with my beams A, B, and ASD. So my beam cannot resist fire for 120 minutes. Alright, let's very quickly check durability, bond, and fire resistance requirements for the beam I'm designing. Fire resistance was already checked. For durability and bond, check. I used the grade C3037, and well, since it will be used as described above here in this example, so the exposure class is going to be XC1. Now, if you go back to that table, you see that for XC1, the lowest grade allowed is C2025, but I'm using C3037, so that means I'm fine. Now let's verify the nominal cover for durability and bond requirements. Again, from this equation, we take the max. So which one is going to be the max? For the XC1, the minimum cover for durability is going to be 50 millimeter, and for the bond, again, what we have it here as we have the bar size as 20 millimeter. So the bond is going to be what? Is it going to be only 20 millimeter? That is not true, because remember, there is the link below it, so it must be subtracted. 20 minus 8 gives you 12 millimeter. Which one is larger? Now in this case, the minimum cover for durability, the 15 millimeter controls, right? And then substitute in this equation. So this is the minimum cover for durability, 15 plus the construction deviation gives me 25 millimeter. Now this is the required one, not my actual one, but I can compare it with my actual one. So let's do it. Now the required one is 25 millimeter. Okay. From the equation for the axis distance A, okay, we already have the value of A. We have it as 50 millimeter. So I want to find the nominal cover. And in order to do it, I just need to rearrange this equation. And if I rearrange it, the actual nominal cover turns out to be 32 millimeter. Now, of course, my actual one, 32 millimeter, of course, it is way bigger than the required nominal cover, the 25 millimeter. So what that tells me is that my beam meets with the durability, bond, and fire resistance. Well, it can be for 60 minutes or even 90 minutes. All of these requirements are met by my beam.